excitations and so on. In principle, you can solve it, but it could be very hard. And the third approach we pursue is to ask the following question: What if we have a wave function? So like we have a wave function on a manifold state. Imagine you have many qubits. Qubits, or more generally qubits. Yeah, those are some local degree of freedoms. You couple them to each other, there's interactions. You get a very interesting wave function on this large Hilbert space with many qubits. And yeah, in a large Hilbert space. And if you prefer to think in terms of quantum matter, you can ask what phase of matter this thing represent, or if this is a gap. And sometimes this is a gapless, then you can ask what kind of critical point or critical gapless fixed point you may have for this system. And there are interesting emergent properties which I'll mention in a minute. But then the physical question would be, if you take a local patch of the wave function, suppose it's large enough, contain enough number of qubits, can we figure out the DNA of the quantum matter, and including all the non-trivial properties, how many anions are there in the system, what's the response of the system to electric field or temperature gradient and so on. Yeah, so yeah, currently there are multiple groups working on this project, and those are some of my major collaborators. I don't think this is a complete list, but in the fusion rules from Entanglement was with Ada Kim and Kotaro Kato, my previous advisor at Ohio State, which we discussed some of the ideas, including how to detect anions using the concept of information convex set. And my collaborators in UC San Diego, my first postdoc, John McGreevy, and the amazing student David Dingjun, Lin, and Xiang Li, and my collaborator now in Caltech, Daniel Renat, Milo Moses, and there are many young grad students in Urbana, Champaign, and other places. We are excited about this program. Okay, so let me sketch you a picture. A picture on different approach to think about quantum matter, and I'll talk about the length scale. So suppose we have some system on a, let's say 2D, but you can imagine that it could work in other dimensions, 3D and so on. And the dimensions, you have many qubits. Many-body system. You have a Hamiltonian, which is sum of terms, local terms. So each of the local terms is supported on some local regions, like a Hamiltonian term, and these are like that. The sum of, let's see, the terms on each triangle or something. But now let's look at the problem in different length scale. This is not too low to see. Oh, I'll try to just use this part. If that's okay. So this is a small length scale. Yeah, you have this local Hamiltonian, but in the largest length scale, okay. Yeah, in the largest length scale, is that okay? We have maybe quantum field theory, and when the system is gap, you usually have topological quantum field theory, which is a gap, and conformal field theory is basically gap-based. Yeah, those are the ideas. Well, we want to usually, well, at least from condensed matter point of view, somewhat traditional condensed matter, but still interesting. It's like you have a Hamiltonian, which is interacting in general. We want to understand what happens at large length scale. There are many interesting things happen at large length scale. Like, let me use a different color. Like, anions. Well, if we talk about 2 plus 1D, 2 plus 1 is like a 2 space dimension and 1 time direction. Then we have anions. And response, chiral response. Well, by chiral response, one famous example is quantum Hall effect. You have, well, in that case, you have some U1 charge conservation symmetry. You have electric field in some direction, then you have current going perpendicular to that direction, and you have some context number. But even without symmetry, without symmetry, you can have anions and chiral respond to temperature gradient. There's something called quantum thermal Hall conductance, and it's related to something called chiral central charge. And currently, usually people need to make an assumption that the action is some integral of Lagrangian, the x dt, maybe to the x direction or something. Or alternatively, people can try to understand, well, no, I guess this part is talk about the particle quantum field theory. So you have a field theory language to describe such phenomena. But more abstractly, you can use the more mathematical language category. Like a so-called unitary modular tensor category and chiral central charge, where unitary modular tensor category is right. So in 2 plus 1D, in the case without any symmetry for gap system, the conjecture would be, if you want to describe the universal properties or the response and the emergent behavior at a large length scale, those are what you need. But in some sense, that's a big conjecture, and people try to prove it from somewhere. But an obvious way people can try to make progress is to go from the left, go from the smallest length scale. So suppose you have some Hamiltonian, you solve the problem exactly and get to answer the question exactly what modular tensor category you have and what's the chiral central charge of the system. But this is hard. Unless you are lucky, unless we have exactly solvable models, some of them you must heard about, called the Taricode models, or more generally the quantum double or the straight net model in 2 plus 1D. There are a large class of solvable models, but there are many reasons we need to do better job than that. First, those exactly solvable models, actually their existence was already a surprise in some sense, but now it's become very clear in the 2010, after like 15 years ago, people started working on this a lot, and people understand what, to some extent, how to go from here to there. I think some audience may have a better idea using operator algebra. You may talk about this later. But the idea is that the solvable models are relatively clear, and we know how to map this to the UV, the smallest length scale, the Hamiltonian, to the universal property at large length scale. But in general, like in 2+1D, if there are non-trivial chiral response, those models will become, at least if you work with the lattice model, those models are usually hard to solve when you cannot say for sure. And the model is detecting the Hilbert space is huge. Even if we try to do numerics, you will usually end up with pretty small system size. So there is a big challenge. Our new approach, the so-called entanglement bootstrap, is built on the idea of start from middle. So start from another length scale. So from the middle length scale, what can we do? We kind of try to do some cost graining. Let me get bigger. Cost grain the lattice. What do I mean by that? What I mean is that I take some large unit cell. So it's like there are many qubits. I choose a cell so that each cell on the lattice contains enough number of qubits. And for gap system, what we usually do is to take the unit cell to be several times larger than the correlation length. And on this length scale, we should, well, at least based on this philosophy, like if you have a large enough local patch, well, I guess the idea is that the IR property, the infrared, is about long wavelengths and small length scale. And this property should still be included in those correlations between the cells without open each box. So once we group those qubits, we treat them as a big cell. We don't talk about how this first qubit in this cell interact with the second qubit, but we only talk about how the cells, the first big cell is correlated to another one, how they are entangled, and what's the geometry of the density matrices and so on. So we will have this kind of tool to deal with this. Okay, so let me make some remarks on what's happening. So first of all, we need some quantum information idea. So we prefer to work with state. So this length scale give us an opportunity to work with the quantum state. And we will borrow some tools from quantum information and entanglement. And this part. So suppose we get some simple roots from this intermediate length scale. Then from intermediate length scale to the large length scale, this program is called Entanglement Bootstrap. And call it EB for short. Yeah. So it's like a start from the middle, and we put some constraint on the wave function and hope to make progress. And in the end, we want to answer the question. Two questions actually. We want to understand. We want to answer two questions. So the first question is like some obvious, like can we extract data of unitary modular tensor category and chiral central chart. Of course, this is for 2+1D. 2+1D. But more general, like in 3+1D and higher dimension, you won't have modular tensor category. But exactly what category framework was the right one was in some sense an open question. But there are some proposals on the market Yes. And yeah, so those questions can be asked in different dimensions. But looking in detail, actually there is a deeper question. It's like why the modular tensor category should be the right thing to consider and why. Okay, QFT, or if you prefer this thing. And C minus describes basis of matter. Yeah. So we are making progress on both of the questions. Yeah, I would say this question 2 is a deeper. And in most of my conversation with the people in conference and so on, we find that the question 1, the fact that we are answering question 1 is well appreciated in the community, but only a small fraction of people understand we are really making progress on part 2. But this question is more important because there are not many options. Originally, well, if you have a Hamiltonian, solving this problem is hard, but then we need to start from quantum field theory. That seems to be natural. Most of the time in the literature, like a lot of people are taking this approach, but there's we need to try to understand what's going on. We need to make some assumptions on which Lagrangian to choose, what field theory might describe the system. But like why this works, and we have some new insight, like completely independent framework. Let's start from the middle. Yeah, that's the main thing we are doing. And after like 5 or 6 years, we feel like we are just get started, not closing the program, but just make it bigger. And each time we finish a work, we feel like we ask more open questions than what we answered. So there's a lot of things to do. Yeah.
So the categorical description of a gap phase is up to invariable phase.
That's right.
So
that's why we added the chiral central charge in something.
But so the non-trivialness of an invariable phase is completely described by the chiral central charge, or
in 2+1D, the conductor is that.
Okay.
Yeah, but in higher dimension, invertible phase will be more exciting, and I will have some comments in some of the later lectures.
I see. Thank you.
Oh, good. That's what I'm tell you in a few blackboards. But let me first draw some pictures. Okay. Let me draw some pictures. Yeah, it's as simple as that. It's not easy to figure out why this should be enough, but it's some entropy conditions. Well, I would say some local entanglement property. Well, those entropy conditions, this viewpoint is well, or you can say this is some entanglement area law, and that was enough for dealing with 2+1D gap system, and you can even generalize this to higher dimension and so on. But if we just look at the entropy conditions, turns out this viewpoint is not enough for dealing with a gapless state. If you want to make progress to gapless state, we need to be, try to change the philosophy a little bit, or maybe appreciate the philosophy in a different way. So we will say local entanglement conditions. Hopefully, I will get to the gapless story in maybe Saturday, and then it will be more clear what I mean by this part. The general philosophy will be guess the right conditions. And each time we if we consider a new physical context, we will change the starting point a little bit. But let me mainly focusing on 2+1D gap system. So yeah, this story for this lecture. So that's already a good illustration. Okay. By the way, so this kind of thing is not happening in the first time in some sense. And we have a similar story much earlier, maybe in the 1970s and the 80s for 1+1D critical system. Maybe you have a Hamiltonian which describes some critical point of phase transition, second order phase transition, and there's some emergent conformal symmetry. So in the small length scale, you also have some Hamiltonian which is interacting, and in some intermediate length scale, you have the emergent conformal symmetry if you wish. And in the large length scale, you have emergent, so the concept of primary state, primary field, and the fusion rules and breathing properties of that describe the modular tensor category of the conformal field theory. There, the guiding principle will be the conformal symmetry acting on the state. But for gap system, we find that the conditions are not from symmetry anymore. So I'm not talking about symmetry, but we talk about entanglement. And in order to talk about entanglement, I will spend maybe both of the slides, sorry, the blackboard, this one and that one, to tell you some tools we will need for some quantum information tool to think about entanglement. Okay, so let me continue from here. So first of all, we consider the Hilbert space. And the tensoring, like let's consider A, B, and C, and so on. So the total Hilbert space of the system would be a tensoring of the subsystems. Yeah, after those two blackboard, I will come back to the axioms. What are the assumptions we start with at the intermediate length scale, or even give you some intuition why we think that that's reasonable and so on. But let me try to be general. So now I'm not talking about any physical context, but we just talk about some general structure on the Hilbert space and quantum state. So here we have a multi-partite system. And suppose the Hilbert space is the tensor product of some Hilbert space. And let's assume any Hilbert space dimension is finite. This is mainly for convenience, but we can relax this later. But for today's talk, I will assume this is the case. And then we talk about density matrices. So density matrices are mixed state. It's a mixed state in the sense that density matrix is usually denoted by sigma, lambda, and so on. is the sum of pure state, probability pi, and pure state psi I, where psi I lives in the Hilbert space of the tensor product. Oh, right. And okay, now let's so given a density matrix, we can talk about something called the entanglement entropy. S of u is minus trace u w. The logarithm is the log of the operator. So you first diagonalize it and make each of the diagonal components the real number take the log, and you get a new operator. So this is an operator times another operator take the tree minus of the tree. At an entropy, the UA is greater or equal to 0. And we can take a if the Hilbert space of any individual subsystem is finite, and suppose you have a finite number of subsystems, yeah, then the total Hilbert space will be finite. That's a good point. Yeah, in some sense, yes. So some people work with the infinite state on infinite plane. Yeah, in that case, you have infinite Hilbert space. But if we look at the beginning figure I draw, if I only look at a density matrix on the local patch, then it's finite. Yeah. And suppose you have a state on A, B, and C, then we can take partial trace and trace out B and C, trace out the union of B and C. You get a density matrix on A. So this rho A will be the reduced density matrix of rho ABC. Yeah. So you can take multiple partitions, you get different reduced density matrix. Then you can consider some slightly fattier properties. For example, you can consider the so-called conditional mutual information. It's defined, this quantity is defined to be a linear combination of entities, SAB plus XBC minus SB minus SABC. And the conditional mutual information. And one important property of it is that the conditional mutual information is always non-negative. The I is a conditional B is greater or equal to 0 for any tripartite state rho ABC. Okay. And I guess I can add a little bit of detail here as well. So the density matrix defined like this one. What's the general property? The general property would be rho is Hermitian. And it's non-negative for any state alpha. And the trace of rho is 1. Yeah. So those properties define the density matrix. And you can check that reduced density matrix is another density matrix. So that is well defined. Yeah. Yeah. So that's a good point. So indeed, the von Neumann entropy is a good measure for bipartite pure state entanglement. If you have a bipartite mixed state, you need some other measure. But nonetheless, as we will see, the conditional mutual information will be some very useful correlation measure. It's like you have multi-party state. We want to understand the correlation, all kinds of correlations. Sometimes this is not sufficient, but it turns out this is a very important quantity for the study of gap space if you want to work with entanglement bootstrap. But yes, this is not the only thing we care. But that's something we need to introduce first. Yeah. The next one, well, yeah, let me also say that a special case of this is when B is empty. Then we get the mutual information between A and C. We define as SA plus SC minus SAC. So yeah, this is the measure of a correlation between A and C. So including classical correlation and quantum part. So it's not a good measure of the entanglement between A and C, but still this is somewhat important, will be important later. And another thing I introduced will be less familiar in the sense that it's not usually introduced in textbook. But let me define delta B, C, and D on any state supported on B, C, and D, the tripartite state to be as BC plus SCD minus SB minus SB. Yeah, so yeah, each of the S with some subindex will be the von Neumann entropy correspond to the reduced density matrix on the subsystem. So the subsystem here is A union D, this is the B union C, and so on. Delta. Okay, so a corollary of a strong subvolatility. Did I say that? Okay. So this inequality is important. So it has a name, a strong subvolatility. Or SSA. And it has many different versions. One of them is the following. And type a lemma that for any state on A, B, C, and D, any mixed state on the four partitions A, B, C, and D satisfies delta BCD of zero is greater or equal to IACD of zero. And in particular, delta would be greater or equal to zero. And because delta is greater or equal to I, and I, the conditional mutual information is greater or equal to zero. So this thing is non-negative. Oh, good. So this is follows from SSA, the strong subactivity. Yeah, so it's some application, but it's an exercise. You need to, yeah, really see how it works. All right. Okay, there's a little bit more, but this well, I shouldn't use this part of the blackboard because of the recording. So let me erase part of this and I think I'll use this part. Right. So in general, multi-partite quantum states are complicated. You have so many different states, and even for the entanglement of a bipartite mixed state, you need to do a lot of work and to only partially characterize the entanglement. So usually that's not sufficient. But then why am I saying this is already kind of useful for some reason? The reason is that it is related to those conditions. I will just wait for a few more minutes to write down the conditions, but let me introduce some very special tripartite state. Tripartite. Markov state. Actually, the quantum Markov state. Quantum. Quantum Markov state. So the definition is this. So UIUC is a quantum Markov state if it's a conditional mutual information until is zero. And quantum Markov state have a very nice properties. And here are something. So the first one is that if we know some Markov state, then it's uniquely determined by the pieces. By yeah, and there's a lot more, but let me start from here. I think this will be enough for the next thing. Okay. Now let's go back to the physical context. So we have some gas system. We try to get some properties of them in the middle length scale. There are some intuitions. I said to solve from the small length scale to the large length scale is hard. And indeed, and in fact, going from the small length scale to the middle is not easy as well. There are lots of open problems. So there are a lot of question marks, including for which Hamiltonian we should have an entanglement area law, and for like which Hamiltonian we should expect some corrections to subleading term or even logarithmic scaling of the entanglement entropy. Many things are not proved, but there are, this is not the larger length scale. So there are numerical studies and studies in solvable models. There are many things people can roughly tell. So there's a lot of things people believe, but couldn't prove at the moment, couldn't prove in the most rigorous way or most general context. But some of them, the belief are the entanglement area law. There are, well, this is a very general terminology, and people working on different research fields have their own definition of entanglement area law. But for me, I'm talking about the 2+1. Let's talk about the 2+1 version, which says the entropy of a disk-like region of the state on the ball, and the ball shape I call it A. It's some constant times the length of the boundary minus the constant. And gamma is a constant, alpha is a non-universal. Yeah, that's some belief, but could be a constant term. So what happens there? So let's look at some implications of this. So first, if we consider a two-dimensional system, so let me draw a rectangle. This is the background. Physical system, we have many qubits here. And we draw regions that are large enough. For instance, and let me start from this very simple one, the A and C. And for this partition, A and C, the mutual information between A and C decays to almost zero. If you want to be accurate, what usually happens is some length divided by some finite number, the correlation length, and L is C, is the separation, the distance between A and C. It's the length between A and C. Yeah. So when A and C are separated far further and further apart, this thing decays to a very small number. And if we want to do theory, we can assume it's to be zero and try to do some theoretical prediction from there. And also, if we okay, I think you start using this blackboard. How about conditional mutual information? If we like take this chain-like structure A, B, and C, the conditional mutual information between a C condition on B will be what? So if we believe the error law, then we find that what this is the entropy of a D, so left a D plus entropy of the state on BC. Minus the entropy on B. The whole thing. And from the error law, we see that any configuration is a disk, and then we look at the boundary. We find that all the boundary are appeared multiple times. Some are in the plus sign. First two terms are in the plus sign, and the last two terms are you have minus and it cancels each other. So we should say they should be zero according to the error law. Then we will say, okay, because of this and the property of the Markov state I'm telling you about over here, then the state on the large disk ABC is determined by the P phase on AB and BC. And you can use this argument recursively. You can argue that the Dixon matrix of a large disk of the gap system, the system with this entanglement error law. Actually, I should distinguish two things. So one is the state with the error law, and another is the gap state. Yeah, I will say they are the same thing for simplicity, but there are some subtleties we need to figure out. But roughly speaking, that's true in the most general case in some sense. But I want to talk about subtleties today. So let me either talk about the area law state or the gap state. I will say they are the same thing, just for now. Okay.
Because a gapless but local theories usually have area law too. So
Okay.
why do you want to say this is only a subtlety? Because it seems.
Oh, good. Because, well, first of all, this is not true for gapless state. The vanishing of mutual information, right?
Right.
Yeah.
I agree.
So the area law I'm talking about is stronger than the area law you talk about.
Oh, okay. You meant mutual information between two regions have to be approaching zero exponentially quick.
Yeah. And yeah, Janet actually was making a good comment because some gapless states also have area law. That's a more geometrical. It's like you have a round ball, right? Yeah, but this is for any shape with a more topological sense of area law. Any other questions? Okay. All right. But now, you can ask what happens for other partitions. Turns out there are interesting partitions that's related to the subleading term gamma, and show some significance of the subleading term is the following. So let's not partition the space only in this chain-like structure, but let's consider a partition originally considered in a paper by Michael 11 and Xiaogang Wen. That when 2005. By the way, they didn't talk about conditional mutual information, but they came up with this quantity, which was exactly the conditional mutual information. And this interpretation is not described in this paper, but later I learned this from Ada Kim. So consider this annulus, partition this into A, B, and C. And we can do the same thing. We consider the conditional mutual information of this region. It turns out from this computation, yeah, let's draw this figure. Yeah, let me just give you the partition without. Yeah, with some abuse of notation, I can read it this way. So the first two are A, B, and B, C. This is B. B is the union of the left disk and the right disk. And ABC is the whole thing. But now if you look at the linear, the subleading one, sorry, the first term, which is proportional to the area of the boundary, that one is cancelled out. But the constant term is not cancelled out. Because from each of the first, so the first and second one, you have minus gamma and minus gamma, and then you have plus 2 gamma. Plus 2 gamma. So in fact, you're left with 2 gamma. And now let me argue that, okay, how is this related to anything that appears in the large length field? So let me try to erase this part and replace this with some figures. So suppose you have some familiarity with the some of the annual models. Suppose you have played with Torah code. Oh, by the way, how many people have know the Torah code model? Okay, that's some people. That's good. But I want, yeah, it's helpful to know the Torah code because it's some concrete wave function to actually have what I say next. But if not, it's okay. It's like the idea is the following. Suppose you know that in 2 plus 1D, some system you should have annuals. From the modern definition by Xiaogang Wen and collaborators, these annuals are non-local excitation. They are non-trivial in the sense that you cannot create an anyon by local operators. You need a string operator. So this is a string operator. And the anyons are, well, your system is in the tensor product of a space. You have your local Hamiltonian. In some sense, it's a bosonic system, but they are emergent low energy particles. If you get the right wave function or right Hamiltonian, then you find that you can create low energy excitations. The wave function are only messed up, changed in the local positions, and the local density matrix around here looks exactly look like the vacuum. a vacuum, like the vacuum like away from the anions. In other words, okay, if you look at the annulus and anywhere, you take any small ball of the annulus, you see nothing. The state is exactly the state with the anion is exactly the same with the state of the vacuum. But nonetheless, if I denote the anion as A, so this is A, and this is A bar, the antiparticle A bar. So the reduced density matrix on this annulus, you have two states. One is the density matrix of the vacuum. Another is density matrix with the anion string passes through the annulus. You have rho of A. Both of them are on the annulus. The annulus should detect the difference. So that means what? So that means you have a multiple state. You have multiple states with the same reduced density matrix. So like both of them reduce to the vacuum state, and call it ρ1 on AB, and reduce to ρ1 on BC. So it's like if you put your anion here, A, because of the string, which might pass through some of the regions, but the string is actually deformable. You can deform the string away from AB and away from the BC. So actually, on the disc-like region AB, you cannot detect the existence of the string, and you don't know about the anion. And on BC, again, you don't see the anion. So it turns out there are multiple states with the same reduced density matrix. What does that imply? So remember that if we have Markov state, quantum Markov state, then it's uniquely determined. Yeah. Determined means it's uniquely determined. So there is a unique state with this property. So if you want to have anions, you want to have a second state with the same reduced density matrix on AB and BC. Then the state must not be Markov. So in fact, A annulus is not the same as U1. We better have we need gamma to be strictly larger than 0. Yeah, so that's some motivation of the connection between the area loss of leading term and the story of having anions. But those are, I would say that this result is
you can recover the density matrix of a bigger region from smaller regions.
Yeah.
But then you say if they all reduce to these two distinguishable density matrix reduce to the same thing, then it means that this reconstruction is not possible.
Right. So
and so then where did gamma greater than 0 come from? I missed that point.
So this IACB on this configuration equals to 2 gamma of the vacuum. Yeah. So if gamma is 0, that means the vacuum is a quantum Markov state. That will be the
Oh, okay. Because you say in reality this cannot be Markov because I cannot recover this ring from these regions A, B, or B, C. Therefore, this mutual information must be non-zero. And because the mutual information is greater than 0, therefore gamma must be greater than 0.
Yeah. Yeah, something like that. Or maybe maybe I skipped something. I think the better or more complete way to accurate the following. So take those two states. You can make another one with a higher entropy. So it's like, for example, you can do a convex combination. Take a half of this, the vacuum state, and the half of the state with anions. By I think it's called concavity of entropy. So the entropy of this one is greater than the entropy of this one. But this one still had the same reduced density matrix. But you can show that if one of the state is already a Markov state, this one will have negative negative condition of mutual information, which is contradicting with strong subactivity. Strong subactivity stated here. Yeah, so that's a contradiction. Yeah, so those are some early motivations. I think I probably gives some enough motivation to think about more deeply about the Markov state, the entanglement property, and the emergent anion theory. Oh, by the way, I would say this result, like gamma is cannot be 0 if you want to have anions is due to adapting maybe the year 2014 around that time. But now in entanglement bootstrap, we are in the position of developing a much more complete framework that start from even simpler condition and derive a lot more. Not only about anions, but later will be about the chiral response, the chiral central charge, and more broadly speaking, is related to invertible state and other. Okay, now I'm going to erase this part and start with the framework. Like
even though gamma is greater than 0, it doesn't say anything about whether it has to be greater than 1 or
yeah.
In a UMTC, gamma is greater than 1.
Yeah.
So will you eventually be able to prove that?
Yeah. We have done. That result is a part of the paper fusion rules from entanglement. Yeah. All right. More questions? Okay, entanglement bootstrap. Now I just started to talking about the modern version of entanglement bootstrap. So with some trial and errors, we were able to pin down the assumptions and make a lot of progress. And so our assumption not in the modern version would be the following. So we have assume some state on a rectangle is a disk-like region. We don't need to have a fancy topology to start with. We only have a many-body wave function on a disk, which is I'll call this as a reference state. Reference state sigma on a local patch, which satisfies some axioms. I'll talk about them, but let me give them some names: A0 and A1. By that I mean the following. We take some bounded radius ball from this large rectangle. Yeah, this rectangle should be large enough. We can think about this as some coarse-grained lattice. Let's see, it's large enough, maybe 100 times 100. 100 of what? 100 of those coarse-grained cells. So if you prefer a hexagon, you can draw hexagon because the purpose is to group the qubits into large cells. Yeah, so you can pick your favorite lattice, either hexagon or square lattice, make sure to have like 100 times 100 large enough, but only finite. Then the total Hilbert space will be finite because it's a tensor product of 100 maybe 100 times 100 subsystem. Each subsystem has a finite dimensional Hilbert space. Yeah, so I think there's a assumption of tensor product Hilbert space. Hilbert space of J and finite dimension. Yeah, those are kind of standard definition. And we are working with 2 plus 1D. That's to say that that's one other assumption to the lattice. But otherwise, we only assume 2 conditions which I introduce. So for any partition of the little ball, we partition the ball into pieces. The first one is partitioned into the interior C and the second boundary B. So on the reference state, we have SBC plus SB minus SB being 0. So we say this is on the reference state, so and the sigma here. And in fact, we can use this notation delta BCD. And this is simply delta B C and the empty set. Yeah. So delta is 0. And another one is some tripartition of the ball. C, D, and D. The second one would be delta B, C, and D is 0. So yeah, one can easily check that those 2 conditions are some compact version of the entanglement area law. Do I have this? Yeah. This formula, but this formula is more hand waving in some sense because you have some non-universal part with second boundary, but this one is some concrete version. We advocate this version of the area law, and you can check them locally because each time you check this on some local patch, and you want the set of this to cover this large region, you check every local piece if the 2 axioms are okay. You say this is a good reference state. We can do entanglement bootstrap with it. Sometimes you can call this as an entanglement bootstrap state. Another comment is that this assumption says that the 2 conditions give you exactly 0, and I commented implicitly that there could be some violation, like some correction, or I guess there was a minus sign. Yeah, so if you want this, you can minus sign. So those axioms will have corrections. So in reality, you only have approximate 0 at any finite length scale, unless you have a very nice solvable model like the Tori code, the StringNet. You do get exactly 0, but in general, you should expect some decaying error.
Sorry. Which one is A0 and which one is A1?
Thank you. So the one above is A0, and this one is A1. Yeah, so in general, we expect some decaying error of the axiom, and if the error decays fast enough, we can have some more robust version of entanglement bootstrap.
Can you say a few things about how you come up with the shape for A0 and A1? I can see that rings and disk are different, and so you want to compute something that contains both disk and contractible regions.
Yeah.
But why this two? Can you give us some intuition?
Oh, good. So yeah, actually that's a long story. There are multiple ways to motivate this, and actually I didn't start from this one at the beginning. At first I started with this one. So like a condition of mutual information is zero. That sounds like a assumption that was reasonable to me when I tried to work on this. And so yeah, indeed those axioms actually imply this condition, so that's a good condition to assume. But this one is weaker than those guys. Yeah. Why is this weaker? Because this one doesn't exclude the volume law state. You can have a volume law state, which will satisfy this one because the volume is conserved. You see, in the plus sign, you have the same volume as those appeared in the minus sign. But those ones are, in fact, more strange in the sense that delta BCD, which I erased, were defined to be SBC plus SCD minus SB minus SD. So the volume is not conserved. So those axioms immediately exclude the volume law state with focusing on the area law state. The topology are different. The topology is important here. And right, so they are independent. Yeah, and comment that A0 and A1 are independent. For instance, we can have a state that violates A0, but not A1. So like some GHD state. So it's like a 0, 0 plus 1, 1, 1. So this state violates A0. A1 is okay. On the other hand, if you have non-abelian anion, like a non-abelian anion somewhere in the middle, C, B, and A, and C, B, and D, so the rest is A. Okay. So, and let's try to consider this one. It turns out A0 is okay. A1 has violations. And more precisely, delta BCD is, for this configuration will be quantized is greater or equal to log 2. So you can break one of the axioms without breaking the other one. Okay. Let me also give some more intuition on the two axioms. The so the first one, A0 implies I in C is 0 for disjoint region B and C. So anything. It can be anything that's outside or separated from A by some distance. A is the local distance. C is the region separated from A by some distance. The argument is the following. You can fill in B. Or maybe let me switch the letters C and A. So like the I in C is less or equal to delta in C empty set. So this is 0 by axiom A0. So 0 is greater or equal to the mutual information. But the mutual information is greater or equal to 0 by subadditivity. a special case of a strong subadditivity. That implies the mutual information must be zero. Yeah, so that's why A0 is stronger than this statement of vanishing of mutual information. Yeah, of course, if you want to be this statement to be robust, you can talk about A0 and A1, two conditions up to some errors. I can approximate. If you prefer, you can have approximate version of A0. That implies the approximate version of this. Right. Oh, yeah, because this one can be true even for volume law state. Yeah, it's not a volume law. Yeah. And we can do a slight change of this argument with A1. So let's try A1. Oh, sorry. I guess I haven't finished A0. So A0, you can came up with another strong subactivity argument that AC conditional B is 0 as well. The similar logic. Sorry, by B I mean the entire annulus. It is not the B shown here. Or maybe let me say B and B, union with B. And this is surrounded. You can see that for the reference state, on the reference state, did I call it sigma? Yeah, I call it sigma. So let me write sigma. On the reference state sigma, this conditional mutual information is 0. It's like you have a state A, B, and C. This chain-like structure, then you can, yeah. So Markov state. Intuitively, what we do is that we use this to deform the region freely.
Sorry. I cannot quite tell this lower picture.
The lower picture?
This picture that you just drew. How does that relate to the picture you drew for A1?
This one.
Yeah. Sorry.
So B, C, this is D. And okay, I guess the rest, I call the rest of BCD the complement of BC and D, I call it A.
Okay.
But we can partition this into two pieces and partition this to be A1 and A2. How about that? So this will be A2, and it's a subset of A. A1, A2, the condition on B is greater or equal to I. A2, the condition on B. And this is another corollary of strong subadditivity. Let's see. Yeah, it's like if we know that for this figure, A represents A1 union A2, the conditional mutual information is already 0. Then we do a partial trace of either A or C. The conditional mutual information won't increase. It will still be 0. So this is twice A2, B, and C. The conditional mutual information will still be 0.
Let me try to see why the regions look like that.
So do we agree that B, C, and D is a partition of a ball that is similar to this one?
Okay. Because they're all contractible, therefore you can draw it in this way, I guess. Okay. Sorry. Okay.
Yeah, great. Yeah, thank you for the question. Actually, let me make some more remarks about this one. This one,
In this picture, why you
some fading elements. Oh, because I want to show you some violation of this A1. So if I put non-abelian elements here, the quantum dimension will be greater than log 2. Oh, I guess I didn't show you the formula. But at the moment, I want to say, well, imagine you have some, yeah, some well, for non-abelian element, there's some fraction of a Hilbert space dimension, if you wish. It carries some degree of freedom, but it's hard to see by itself. But nonetheless, it will show up in the fraction of entropy. It turns out for the region B UIUC, yeah, for the computing of this term, S of BC, the region B and C contain the anion. So you have an anion here, the entropy is actually increased by some amount. And it turns out the increasing is quantized in some way. Later we will be able to show that. And the smallest number, so if this is non-zero, the smallest number is log 2. Yeah.
So A0 and A1, you want to exclude excited states as well.
Good question. Yeah, yeah, that's a good point. So I should comment on this. So some naive way of understand A0 and A1 would say, oh, you have a local Hamiltonian with a gap, and then the ground state should satisfy A0 and A1. That statement is actually wrong. We are not talking about the unique ground state of a gap Hamiltonian. Rather, we talk about some clean state, like free from any dust and excitation. So we want to detect the cleanness of the state by the axiom. So we take a piece of the local density matrix, we check all the axiom. If the state satisfies all the axiom, we say, oh, this is a clean state. Or if we wish, we say this is a fixed point. Yeah, actually, I'm going to talk about the fixed point viewpoint around here.
So it's not about it's just to see if this particular state looks like some state without excitation. Order, but I don't care where it came from. But
yeah, yeah, that's one viewpoint. Yeah, yeah, we don't care about the Hamiltonian. Let's just try to classify states. Ask how many interesting states are there and how they are classified up to some equivalence condition. So we will specify this much later.
So you're trying to say that A1 is trying to express that I have a region with a deformation slightly deformed.
Yeah.
Is equivalent.
Yeah. Space. This is a local job. I'll explain this in better way, hopefully in this platform. Okay. Now I'm going to talk about length scale again. So it's like we have a small length scale, an intermediate length scale, and large length scale. But suppose we have a state with the axioms satisfied on some length scale. So let me draw really small. So the axioms, suppose they are already okay on some length scale. And then we do RG. RG means renormalization group loop. Well, RG is a very general idea, but here the idea I'm talking about is to cross-grain the lattice further and looking at the larger length scales. Now we would be interested in checking the axioms on much larger balls. Yeah, so those are smaller. This is some large R. It turns out we can say a few very simple things about the axioms. So first, use the axioms A0 and A1 both on the small length scale R. Then by strong subactivity, A0 and A1 also both on the larger length scale. So yeah, in that sense, it should represent some RG fixed point. And furthermore, I want to explain better on this aspect. So why axiom A1 represents some space homogeneity, why it says the state must be uniform. So there is a sense that axiom A1 helps us to deform the information from some part of the system to some other part of the system. Yeah. A0 and A1 and strong subactivity. Yeah. So it's like yeah. I think I'll probably skip the proof. Maybe we will come back during the tutorial or okay. Or maybe the next lecture, depending on the detailed plan. Yeah, but this is worthwhile to spend a few minutes.
Very important point.
Yeah.
So how you can see RG in this process. I'm very.
Oh, great. And okay, so this is about RG length scale. And then let me talk about deformation of the region, some space homogeneity. And let me illustrate this point by the quantity called topological entanglement entropy. Topological entanglement. Oh, by the way, I saw someone is leaving at 11:30. Okay. Okay, I'll continue a little bit further, but let me give you a sketch. So it's like the topological entanglement entropy can be computed with some partition on the background. So you have a large system, you compute some linear combination of entropy on the local disk, and you get some number. This is the value gamma. In the end, we will show that the sublinear term gamma will be quantized. It can be 0, it can be some other things, but there will be some other values we can exclude. It can never exist due to the consistency with the quantum mechanics. But before showing that, I want to show you that actually axiom A1 implies that the value gives the same answer whether or not you compute from this part of the system or another part of the system, and you can even define the region topologically, ABC, A prime, E prime, and C prime. So A1 implies that gamma computed on the left side, A, B, and C, equals with gamma computed on E prime, E prime, and C prime. How do we show that? The idea is to deform the region step by step. So each time we deform it a little bit, the kind of deformation we use are exactly from this figure. So it's like we have A, B, and C. This region is B. and you add a little local bump near the entanglement boundary, and so the region is deformed. And we can do the same thing here. Let's look at the A, B, and C. Let's add a little bit. Let's call it maybe C prime. We want to show that gamma computed from ABC equal to gamma computed from A, B, CC prime. Yeah. It turns out this boils down to some simple mathematics, like the dimension of. I think one thing is that the dimension of yeah. So maybe I should go through this mathematics and yeah. Defined by Tsinghua and Pascal in 2005. You have 7 terms. That's AB plus BC minus B plus AB. And then we take a difference. So if we have this A, B, C prime minus gamma of A, B, and C, what do we get? And so whenever we see a term without C, we don't care about it. So which terms are related to this one? We have 4 of them, right? So when we look at SBC, we replace this by C by CC prime. Minus. Okay, we have 8 terms. We probably need some clever ways to repeat them. C. Prime. Okay, let me try to group those 4 terms. These 4 terms give you some conditional mutual information. Like C prime B condition inside B, yeah, condition on C. How about the other 4 terms? 1, 2, 3, 4. Basic. Okay. I think the other one. Oh, sorry. I think the yellow term should be minus one. And then I think the other, if we do group the other 4 terms, we have plus sign and C prime the condition on AC. Yeah, but both of the terms will be 0 by strong subadditivity and axiom A1 using exactly the same argument here. And remember that we have argued that A1 axiom A1 holds on all length scale. So yeah, that is enough to look at this one. So on this circle you have A1, then both of the terms will be 0. All right. Yeah. So yeah, that's the intuition I want to emphasize. And this will be emphasized again and again in more exciting ways in the later lecture. That axiom A1 is some space homogeneity and deform region from one place to another, and this state in this local ball is not so different from the state on the other side, as long as all the axioms are hold. All right, so I think I'll take the next 10 minutes or 10 to 15 minutes to tell you about two things. One is the philosophy of Bootstrap. I'm going to emphasize that we're actually deriving some constraints about quantization of something based on some those more structureless conditions. So we have A0 and A1, they are saying some kind of entanglement area law is true, and you have some space homogeneous state, some nice state. But from those constraints, we can actually derive something is impossible and some quantization. Some are theorems, some are conjectures. Then I'll introduce the concept called information convex set to talk about the anions more precisely. Then we'll end the lecture. Okay, so now the game of entanglement bootstrap is summarized as you have a reference state and with two axioms, and this version is in two dimensions, tensor product Hilbert space and finite from local Hilbert space. Okay, so start from there. We are to remember that the original goal was to say, or given a reference state, we want to map this to some unitary modular tensor category and chiral central chart. Suppose the conjecture classification is the right one. So suppose it's correct. We are very ambitious. We want to rederive this classification. Of course, if this turns out to be incorrect, we should be able to point it out. But on the way of doing that, we already find some hints that we can sort of compute some quantity from the local regions. So like you have a state, you have a Lagrange ball. Here, it seems to be at the DNA of the base of matter. For example, gamma. Okay, this is one example. But now let's imagine we have a collection of a different reference state. We can ask the question: what value of gamma can exist? Values of gamma is allowed. Then we draw this axis. So this axis of gamma, or maybe more conveniently, into the 2 gamma. And if we believe this unitary modular tensor category, and believe a formula, gamma is the logarithm of the sum of anion quantum dimension If we believe that, then we will conclude that the smallest value is the one. Sorry, I think yeah, 2 gamma is this. And then the next smallest one is 2. And there shouldn't be anything. So this should be excluded. And this one is this part is excluded as well. And so yeah, we can be more precise. Yeah, but those are the things entanglement bootstrap is trying to do. They try to tell you which values are consistent with the constraint of a quantum physics. Yeah, suppose you have an area law, then the subleading term can be this one. It could be this one. It could be another one. Okay, I think you go this thing e to the 2 gamma equal to 4 as a wave function is the Tauri code. And Tauri code is here. And this one is the trivial product code. This one. This one is more subtle, something called chiral Samuel. So you have examples of many body wave function topological ordered state ground state, which give you some of the values. But on the other hand, in entanglement bootstrap, we are making progress in the other direction. We want to prove that some other values can never exist. So like you have more and more examples. But on the other hand, you say something is impossible. And in the end, if we have both of the approach, hopefully you can reach the classification of phase of matter. You will see, oh, there's no more and there's no less. Okay. But this figure is only the tip of an iceberg. The reason is the following. So look at this one. So this 4 number, total quantum dimension, the sum of any species equal to 4. Well, there are multiple examples. One is the Turing code. The Turing code can give you this number of total quantum dimension. But there's another model called double Samuel. Give you the same total dimension. So in this figure, they are degenerate. You have multiple different phases of matter. Well, they are inequivalent to each other. You can not convert one state to another by finite depth local circuit. They have different anion gradient statistics. You can have different ways to distinguish them, but nonetheless, they have the same anion content. And actually, there's one more. It's called the eating anion theory. Eating anion. This one is chiral. But the other two are, thank you. 8 of them. 8 of them. Detected by different gradient statistics. Is that right? F symbols. Okay. Great. And this one is non-chiral. Yeah. So if we only compute the subleading term of entanglement area alone, we certainly learn something, but that's not everything. So that's just the starter of a appetizer of the entanglement bootstrap. I will talk about chiralities hopefully in one of the later lectures. But before that, I will tell you about how we derive the anion, how we define anion species and the fusion rules from a single wave function. And yeah, the last part of today's lecture will be a definition that gives you some structure. some structure beyond the total quantum dimension. So for that purpose, I'll go back to the annulus picture, the annual information convex set. So remember, we have a figure about the annulus. So this annulus region, let me call it omega. The omega is embedded in the background. The background rectangle, we have this region embedded in it. Let me do this without drawing the background, but imagine it's embedded in the background, and we can consider a convex set of density matrices. Or the information convex set. Sigma omega defined as a set of state omega with some conditions. And what are the conditions? The condition says so that on the thickening defined as the thickening of omega. Thicken the annulus a little bit and look at the ball that is contained in omega plus. So this is the omega plus. It thickens omega, so it contains omega, but it also contains the qubits leading within some distance to omega. So the thickening of omega, there's a state rho tilde omega plus, such that rho tilde reduced to any ball equal to the reference state reduced to the ball for any ball contained in omega plus, and rho omega is obtained by the partial trace omega plus minus omega of rho tilde. Well, omega plus. Well, I guess this line is just saying we have omega tilde on this taking the annulus, but we reduce it back to omega. Yeah, this gives you some state. And the information convex set will be the set of all such states. All such states satisfy this property. So the state can be thickened, and on the thickening, it locally agree with the reference state. So it's a set of locally indistinguishable states. The intuition is a set of the and we shall prove later in this one. Proposition is that the information convex set of the annulus will always be a simplex. And from there, we define the annulus. Yeah, and this confirms the previous intuition of a annulus string. So the annulus in the middle, you give you a different state, but we will have a more precise statement, including that you always have a simplex, and the fact that all the corners or the extreme point of the convex set, those states must be mutually orthogonal. If you take any of two of them, you find that they are orthogonal. For example, by computing the fidelity between the two states, you will find the fidelity is approximately 0. That means the states are approximately orthogonal. But and the exact version of the axiom, you can prove the exact orthogonality. So the states are perfectly distinguishable on the entire annulus, even though if you reduce to any disk-like region of the annulus, you see no difference at all. They are the same, but globally they are different. So the difference can be seen only topologically. Yeah, let me just quickly write down some consequence of this one without proving. Okay, so this one is trace omega plus minus omega. Yeah, so I'm tracing out the shell, the second part. The information convex sets can be computed on different regions. Actually, the simplest one is on a disk. The information convex set of disk will be just the reference state on the disk. For any disk embedded in the background. So it's like you pick any disk, you don't see any difference. And so if you have a region that's a union of A and B, and you have some state belongs to it, then if you take a partial trace of B on your B, this state will belong to the information convex set of the subsystem. And as I said, information convex set of an annulus will be a simplex. So each extreme point, the extreme point will be labeled by A anyons. And we define anion this way. And that of the two-hole disk will be using the fusion space. Yeah, the fusion space will be detected by the information convex set, the set of locally indistinguishable density matrices on two-hole disk. Well, intuitively, why this could work? So the annulus is topologically equivalent to a cylinder. And the second cylinder is like, if you are familiar with calculus, it's like an anion string, like a second version of this. And the two-hole disk is almost like this one. By this tutor, what I mean is, yeah. By this tutor, I just mean they are homeomorphic. Homeomorphic, the Chinese would be 同配. Yeah, they are the topologically the same in that sense. And in this diagram, you can imagine anion A, B, and C, and there are some fusion space. Yeah, it turns out we can prove theorems about this and rigorously define the anion species and the fusion space, and do a lot of more. To tell you how to understand all such things. Given the wave function within the ball, so we only need the wave function within the ball to talk about them. That's because every region defined here is embedded in the background. So as long as you have a large enough reference state, in principle, you can do everything I talk about in the next few lectures. And thank you. I think my lecture ends here, and I will be around to answer more questions.
Sorry, I have a question. Can you hear me?
Hello.
Hello.
Yeah, I can hear you.
Yeah, I'm talking online. So I'm confused about the motivation of so-called thickening.
The motivation of what?
Thickening.
Thickening.
Yeah. Why we should do some operations?
Uh-huh. Okay. Yeah, that's a good question. Good question for the tutorial if we want to answer this more fully. So if you can come, please try to come. But let me give you a sketch. The sketch is the following. First, there are multiple equivalent definitions of information convex set. The one I sketched here, the thickening. The advantage here is that you can have a local constraint on top of the thickened state, the state your tutor, you have a local constraint on that. That's enough. But the other, some alternative version, which we put in the appendix, I believe appendix C of our paper, were to do without thickening. And in that version, you need to assume some quantum Markov state condition near the thickened boundary. So in other words, the subtlety happens in a entanglement boundary. And intuitively, why that's the case? Well, yeah, maybe let me give you one example and one motivation, one other more abstract motivation. So the example is the following. It's like you have some state. Let's say the state is made of a bell pair, bell pairs. So that the entanglement is very simple. You have only local entanglement. And without assuming the thickening, it turns out you can have a state in a, let's define this as a sigma tutor omega. That's the information convex set, the more naive version of information convex set without doing the thickening part, the thickening step. Then you can entangle the bell pairs. Originally, they are entangled with something else, but now you can imagine you have a state which with them entangled with each other. Oh, I think not those ones, but those ones that are separated more far away. You can somehow entangle them. Then this is a larger set. This is a larger set. And in fact, it's strictly larger. And when your region becomes larger, this set is larger. The size goes up with the size of the region, and we don't want that. We want a set instead. We want a set that's stable under deformation, so it's invariant in the following sense. So we want the set to be isomorphic from this one to another one if omega can be smoothly deformed to omega tilde on the background. So yeah, that's the idea of the transportation. So you have an annulus, you call it omega, and you deform this to another place, make it larger, and deform the shapes and so on. Omega prime. You want the two sets to be of the same size in a very concrete sense. It turns out we either need to thicken the annulus a little bit or use the alternative version that's in the appendix of our paper.
Does it means if two omega and omega prime are only differ by some boundary transformation, then they will give same information convex set?
Yeah, that's a theorem we will be able to prove.
I see. Thank you.
Thank you. Let me see. So you want a 1 plus 1D gap state or gapless state? Your state looks like some CFT state. It appears to be gapless, and at a larger length scale, it will flow to some gap state. Yeah, that RG flow is some ongoing direction of entanglement bootstrap. Yeah, we have some numerics, but the proof I talk about mainly works on fixed point or approximate fixed point. And I will talk about some gapless fixed point condition which are different from those ones. I think on Thursday. Oh, sorry, Saturday. Yeah. Good. Yeah. the axiom A0 and A1 have some direct analog in 1D. So the idea is that you always have some balls. So those are two-dimensional balls. In 1D, the one-dimensional balls will be an interval. And the region in the middle will be the center, the interior of the region. And the B and D, the other partition, will be on the second boundary. Yeah, and we have a three-dimensional analog, all higher dimensional one. So it turns out we believe we only need two conditions. Well, I guess in 1D, these two are not independent. You end up with only one of them. From one of them, you can derive the other. But in higher dimension, you don't add more assumptions. You always have two assumptions. Yeah, will be. I think it will be trivial. If you want to study the version of entanglement bootstrap system with symmetries, you need some model assumptions. So those assumptions we take are about entanglement structure. The density matrices, we didn't talk about symmetry at all. But if you know you have SPT, then you know the state preserve the symmetry. And that's another condition you want to put on top. So we have more assumptions you need to add to the list. Yeah, so currently we have reference state A0 and A1. But for with symmetry, we add another one. Like the state is symmetric, roughly speaking. Okay, so if no more question, I'll follow Jenny's instruction to stop the recording.